We're going to have a bit of fun with proof by contradiction. See if you can pick up the basic structure. If you don't pick it up, I will formalise it at the end of the video. But let's say we're required to prove that root 2 is irrational. Now you may have learnt that as a fact, but have you proven it? Contradiction is one form we can use to prove things, and we're going to use it here. So here's the proof. Let's assume that root 2 is rational, the opposite. That would mean that root 2 equals a over b, where a and b are integers and a and b have not any common factors, apart from one. And of course b cannot equal 0. And continuing the sequence above, let's square both sides. So if we square both sides, we've got 2 equals a over b squared. It's all squared. So 2 equals a squared over b squared, using the axiom of the index laws. And rearranging, we have 2b squared equals a squared, and we might call that result 1 because we're going to refer back to that. This means that a squared is even. And a squared can only be even if a is even. Now that's possibly debatable at this stage whether that's an axiom or it needs to be proven. Depends on the level of maths you're doing. So let me prove that with a subproof. For a, we're going to prove by contradiction in a subproof if a was, let's suppose a was odd. So assume a is odd. A equals 2k plus 1. A squared would then be 2k plus 1 all squared, which is 4k squared plus 4k plus 1, which is 2 outside of 2k squared plus 2k plus 1, and that's the form of an odd number. So if a were odd, it would give an odd number when it's squared. So therefore it's not derived from an odd number, it's derived from an even number. If it was derived from an odd number, you would get an odd number when it's squared. So back to the main proof. Cordon that off. If, back here we said therefore a squared is even, and therefore a must be even. So yes, a is even. So if a is even and we use statement 1, and letting a equal 2c, I'm not going to use k again, I'm going to use a different letter where c is an integer. We have 2b squared. Now in statement 1 it says a squared, so we're going to make that 2c squared. That's all squared, replacing a with 2c. And 2b squared will equal 4c squared. Then we have b squared equals 2c squared. Therefore b squared is even, it's divisible by 2, okay? Therefore b is even from what's now an axiom. Now let's compare a and b. A and b are both even. Now this contradicts what we said up here, namely they don't have any common factors. So it contradicts our original hypothesis. Okay, that they had no common factors, because even numbers have at least 2 as a common factor. Hypothesis is wrong. Root 2 is not rational. It can't be expressed as a rational number. Therefore, root 2 is irrational. Okay, because QED, so that's a D. Basically, remember with these sorts of numbers, they have to be able to ultimately be expressed as integer over integer, and that's after everything's been cancelled out, and we've shown that these ones cannot be. Perhaps it's a property of these numbers that wasn't expected to be exploited, but it's showing that the hypothesis is wrong, so it's pretty much exposed that as a bit of a joke. So that's been disproven. So proof by contradiction proved the opposite situation. So we've proved that it's irrational by disproving the folly, using the folly that it's definitely not rational, all right, and therefore it has to be irrational because a number is either rational or irrational. Formalizing this, a proof by contradiction can be used to prove that something cannot be done. And that's what we did just then. It's proven that something cannot be done. We just did that. Assume that the statement we want is false. Show that this assumption leads to some sort of absurdity or dysfunctionality, nonsense if you like. Conclude that it would be wrong to assume that that statement is false, okay? And then conclude that what we're trying to prove is true. So proof by contradiction can be used in a number of ways. One last quick example. So if 5 to the x can be solved, 5 to the x equals 2 can be solved for x, and if that satisfies the equation, prove that x is irrational. Sorry, I've just fixed that up quickly. It should be irrational. Okay, so assume the opposite. So assume x is rational. This is the proof by contradiction, step 1. X would then equal integer over integer, a over b. A and b are elements of z. Okay, a and b, no common factors. B doesn't equal 0. Alright, so subbing that into the original equation, we've got 5 to the a over b equals 2. Now here's the trick. If we raise both sides to the same power b, on the left hand side using index laws, power of a power, we'd have 5 to the a equals 2 to the b. 5 to the a is always odd. 2 to the b is always even. Okay, this is a contradiction. That hypothesis is wrong. Therefore, x is not rational. X is irrational. Proof by contradiction.